Section 8.2, what affects the margin of error? In the last section, we covered an example where we were given a confidence interval and asked to interpret it, and we said that we were 95% confident that the interval from 10% to 18% captures the proportion of all US adults who would say healthcare costs are the biggest financial problem facing their family. The claim 95% confidence means that we're using a method that will successfully capture the parameter in 95% of all intervals created using this method. So let me take a second to explain that. On the right here, we have this image that has a number of different confidence intervals. This one right here, we can see that dot is representing the result of the sample. The lines that move out from the dot are representing the margin of error. And we want that population P, that green line that goes down the center, to be somewhere in the range of the beginning and end of that black line. Now note that every time we take a sample, we get a different result. That's why those circles are kind of jumping around that green line. But what we're hoping is that when we make the interval, the start of the black line to the end, that this P is somewhere in that interval. If we're making a 95% confidence interval, about 95 of every 100 intervals that we create will have that green line in it, but sometimes we'll miss it like we do in this one right here, denoted by that red line, or this one down here. All the other ones that are black correctly capture that true population parameter inside the bounds of that interval. And that's what it means when we say we're 95% confident in the range of values that we have for our interval. That's the confidence level, and we're often going to be asked to interpret that level, and we're going to do so with a form answer, just like we do when we're asked to interpret the confidence interval. So if we're asked to interpret the confidence level, we would say something like this if we were to select many random samples from a population and construct a C%, 95% confidence interval using each sample. About 95% of the intervals would capture the true proportion of adults who would rate healthcare as their primary concern. Now note this is different to the form we used in the last section where we said we are 95% confident that the true proportion of all adults who would rate healthcare as their primary concern is in between 10% and 18%. Make sure you're giving the right form answer depending on the question. Interval versus level, two different answers. Level is this one right here. Interval is the one that we did in the last section. Confidence levels are about all intervals. They're about the process of creating intervals. Where we interpret a confidence interval like we did in the last section, we're talking about a specific interval, which will include those specific values in our response. The National Center for Health Statistics asked a random sample of 3,626 US adults about a variety of topics. According to the study, the 95% confidence interval for the true proportion of all adults who eat fast food on a given day is 35% to 38.2%. Interpret the confidence level. Again, the level is about all intervals. It's about the process of creating intervals. Every time we take a different sample, we're going to get a different p-hat, and with each p-hat, we're going to get a different interval. So when we interpret a confidence level, these numbers are not going to be in the answer at all because they don't have anything to do with the level. The only thing that's going to be in our answer is this with some context. If the National Center for Health Statistics selects many random samples of US adults and constructs a 95% confidence interval using each of those samples, about 95% of those intervals would capture the true proportion of US adults who eat fast food on a given day. One thing that gets a little confusing is that the confidence level is not telling us the probability that a particular confidence interval captures that population parameter. So when we make an interval, like we have here, we'll pick the one on the top, we either get that confidence, that population parameter in the interval, or we don't. Either there's 100% that it's in it, like it is here, or a 0%, there's no in between. So that 95% is not about a single interval. it's about all the intervals collectively, and the fact that 95% of all of those intervals will capture that true population parameter denoted by that green line there. Generally speaking, we want thin, short, or narrow confidence intervals. In other words, we want confidence intervals that have small margins of error. Knowing that tomorrow's high temperature will be between -40 and 200 degrees Fahrenheit won't help you pick out your clothes in the morning. But if we know it's going to be between 80 and 82 degrees, that would be a useful interval. So when it comes to reducing the margin of error, we can change two factors. The first is the sample size, and the second is the confidence level. And let's talk about the confidence level before we talk about the sample size. So we can change that 95% to 90% or 99% or 80% or whatever we want really. And just know that the price we pay for greater confidence is a wider interval. So if we have an 80% confidence interval, we'd be looking at something like that versus a 90% confidence interval or a 95 or a 99. So you can see as our confidence level goes up, the interval gets wider, which logically makes sense. If we're more confident that this green line is in the bounds of our interval, we need to have a bigger interval, a bigger stretch of area covered by that green line. We're less confident that it's in there when we have a shorter range for our interval. And we see that when we interpret that confidence level like we did on the earlier slides. For an 80% confidence level, we're going to capture that true population parameter in 80% of the intervals, which means we're capturing it in about 8 out of 10, and we're missing it in about 2 out of 10. If we up that confidence to 99%, we're going to capture it in 99 out of every 100 intervals we create, right? Mostly because it's so much wider of an interval. Note that all of these p-hats, these dots, are in the same place. Okay, it's only the width of the interval that's changing, and that's determined by that confidence level. The other way that we can adjust the width of an interval is by changing the sample size. Larger samples means we have narrower intervals with smaller margin of errors. If we look at both of these displays, you'll see that the confidence level is the same in both. They're both 95%. But on the left, we have a sample size of 20, and on the right, we have a sample size of 50. Okay? As we increase that sample size, we see that the width of the interval gets much smaller. We have thinner intervals while keeping that same level of confidence. Now, generally speaking, we always want to take a larger sample. However, larger samples cost more time and money. In general, we want our confidence intervals to be as thin as possible. So the two key things to note is that the ways that we can make that thinner, make an interval thinner, are by decreasing the level of confidence, right? Which means we will have a thinner interval, but we're less likely to actually have that population parameter within the bounds of our interval. Or we could increase the sample size, which is going to shrink that interval without sacrificing our confidence level. However, that's going to cost more time or more money. So let's go back to our sample of 3,626 US adults who were surveyed by that National Center for Health Statistics. We got a 95% confidence interval for the true proportion of all adults who eat fast food on any given day, being from 35% to 38.2%. If we change this interval from 95% to 99%, what would happen to the width of the interval? Well, it would get wider. The confidence interval would be wider because as our level of confidence increases, we're going to be more certain that that true population proportion is within it. And because of that, we need to go out a farther distance on each side of our point estimate, which again, from last section we learned is right in the middle of those two endpoints of the interval. What would happen to the width of the interval if the sample size was increased from 3,626 to 5,000? Well, bigger sample sizes mean we're going to have less variation. We're going to have thinner intervals, so the confidence interval would be narrower. increasing the sample size is going to decrease that margin of error. So when we make a confidence interval, we're not providing an exact estimate. We're always giving a range. And on top of that, we're tying it to some confidence level where we're saying we're this % confident that it's in this range of values. All of those are affecting the margin of error, which is accounting for the fact that our samples will vary. If we take a different sample, we're going to get a different result every time, as indicated by here on this graph, and all the different X bars we get when we take a sample of 50 pennies and average their years. Now, there are other sources of variation that confidence intervals don't account for, such as biases. If we have any kind of bias in our sample collection, such as voluntary response bias, selection bias, etc., our confidence interval won't necessarily be correct. As part of a project about response bias, Ellery surveyed a random sample of 25 students from her school. One of the questions in the survey required students to state their GPA out loud. Based on the responses, Ellery said that she was 90% confident that the interval from 3.14 to 3.52 captured the mean GPA for all students at the school. Why did Ellery include a margin of error with her estimate? It's because of sampling variability, the fact that different samples of the same size are going to give different estimates, and we'll get a different average GPA for every 25 students that we talk to. Describe one potential source of bias in Ellery's study that's not accounted for by the margin of error. Well, it has to do with the fact that these students were asked to state their GPA out loud. They may be embarrassed about a low GPA, and because of that, they might lie about it to make themselves sound better. Our margin of error is not going to account for any bias within the way we collect our sample.